Hey everyone, welcome back to Pseudocoders. This is Ravina. Today we are gonna talk about the two important algorithms, breadth first search and depth first search. You'll be using these algorithms to solve many algorithm problems. So these algorithms are basically used for traversing or searching through a tree or a graph. Now let's hop on to what DFS is. In DFS, you basically start from the root node and explore as far as possible along each branch before backtracking. So what it means is that let's take an example. Like we have this tree in front of us where 5 is our root node. So we want to explore along the branch as far as possible. So let's try and explore it from left to right. So if we are here on the root node, we can explore, we can go. Do we have anything on the left hand side? Yes, we do. We move to 3. We check if is there anything on the left hand side. Again, yes, there is. We move to 1. And now, after reaching 1, we again check if there is anything on the left hand side of the tree. Is there anything? No, there is not. So we move back to our root node. Now we can, in order to display this DFS, I can just, and then we just explore this element, which is 1. We can print it. Now we go in and check is there anything on the right hand side of the tree. There is not. Then we come back here. Now this node is processed. So we go back to 3. We check if we process this element 3. Now we check if there is anything on the right hand side of the tree. There is. We can find 4. So we come here. We check if anything on the left hand side. No, there is not. Go back. We are again at 4. Now we process this node. We go and check if any is there anything on the right hand side. There is not. We move back to 3. Now 3 and all of its children are processed. So we move back to 5. Now we process 5. We check the left hand side of 5 is already processed. So we check if there is there anything on the right hand side of 5. Yes, there is. We go to 6. On 6, we check if is there anything on the left hand side of 6. There is not. We come back to 6. We print it. And we check if is there anything on the right hand side of the tree. There is not. Then we go back to 5. So this is how you process a DFS on a tree. We can also do it using a graph. We also use it for traversing a graph, right? So let's take an example how it can be done for a graph. Let's say you have A, B, C, D, and then you have E. Now for this, suppose our root element starts from here, which is A. So let's write our DFS, how our DFS is going to traverse. We can go and check, go to D. We check if is there anything on the left and right. Do D have any depths, more depths available? No, there is not. We can just print D. We go here and then we move back to A and we check, uh, we move back to A, then we basically explore that A. Now we check if there is we go along this path which connects to C. Now we check is there anything, does C have any more children? No, there is not. Then we can process C. We go back to A and we check if is there any other neighbor, is there any other children of A present? Yes, there is. We go to B. Okay. Yeah, so we go to B and now we check if is there B does B have any children? Yes, there is. We go to E and now we see if E has any children, though there are no children. So we process E, we print E, we go back to B and then we print B. So this is how basically the depth first search works. It explores all the elements on that branch before backtracking. So where is this backtracking happening in our case? In our case, if you notice, we go from A to B. We don't process B. We go to C. We go to E directly. We process E and then backtrack and then process the root element. So this is basically how DFS works. DFS has 3 types: in order, pre-order, and post-order when you're working with trees. So what does a pre-order mean is that the root node is processed first. So we have three suffixes here: pre, in, and post. So it's basically pre-order, in order, and post order. So what the pre-order means is that the root is explored first, then the left element, and after that the right element. Whereas in order, you process the left element first, and then the root, and then the right element. Whereas in post order, you have left, then you have right, and then you explore the root element. So these are the three types of DFS. The one we used for our tree is in order because we explored the left first, then the root, then the right. So if you see, we were going all the way to the left and then process the left element, then right, so left element, then root, and then right. So this is how the DFS works. Now let's have a look at it. You can implement DFS using recursion as well as using stacks. I have written a small code for recursion. So let's see. This is the tree node, where the tree node has three attributes: value, left, and right. The value holds the value of the node. The left denotes the left pointer. The right denotes the right pointer. Now, what I did is I just created a root node uh, and just defined the tree here. Now let's go to what our DFS function looks like. So we always need a base case in case of recursion. So what if we hit null? So in our case, if you see, we are hitting null here, right? When we check if there is anything on the left-hand side of the tree, then what do we have to do in that case? We just have to return. So this is what I have written here. This is in Python. So I check if there is no root, then return. So it basically means is that if the root is null, you just return. Otherwise, you just call DFS function on the left-hand side of the tree. That means you just go left. You Once you have gone all the way to the left, what you do is you print the root value that is there, and then you go to the right. So it's basically the same thing that we did. We went all the way to the left, and then we just printed the node value and went all the way to the right. So this is how a DFS function looks like. Let's talk about the time and space complexity. So if you see, we are visiting each node once. So that's why our time complexity would be O of n. So n being the number of nodes in the tree, because we are traversing each of them one. So the time complexity would be O of n. Whereas when you talk about the space complexity, you are so when you talk about the space complexity, it's basically the height of the tree. So why is that? It's because you are traversing through one branch at a time. So you're exploring the branch all the way to the end. So whatever is the height of the tree, that would be the space complexity, because that is the maximum memory that we are using. So the space complexity would be O of h, where h is equal to height of the tree. I have written it here. So yeah, so the DFS space time complexity is O of n, whereas the space complexity is O of h. Um, so let's talk about the uh, BFS function. So what is breadth first search? Breadth first search is basically an algorithm which is also used for traversing through tree and graphs. It basically explores the tree on the basis of levels. Also, it can be known as an algorithm where it explores all the neighbors first and then go to another level. So what do I mean by that is, if you have the same example into consideration, where I have 2, 3, 6, 1, and 2. When we do BFS, what it will do, it will start with the root node, see how many explore all of its neighbors, so which is 3 and 6, and then explore all of the neighbors of 3 and 6. So if you go in and print that, you will get something like you have this level printed first, and then this level printed second, and then this level. So let's apply a breadth first search algorithm on this tree. So let's start. If I give an example, you'll understand better. We start with 5, then we process the 5 because that's the only root we have. So process 5. Now on level, this is level 0, this is level 1, this is level 2. Now level 1, I see 2 nodes. So those will be 3 and 6. And then going back to level 2, it has 2 nodes, 1 and 2. So BFS is pretty simple when you visually look at the tree, and you can just write down how the tree would be traversed in case of in case of breadth first search. When you take into account the graph, so let's also talk about graph because we are exploring uh, graphs and trees for understanding the algorithm. So I have breadth first search. Now, uh, let's start with A. A is our root node, so we process A. Now we explore all the children of A, that is all the neighbors of A. So I have B here, I have then C, I have D, and then we go and explore all the children of the processed elements. Now, once these are done, I can just use a different color maybe. Um, Okay, so I have processed A, I have processed B, C, and D. Now I'll process B, all the children of B. So all the children of B is E. So I'll just process E. Now I'll go to C. I'll check if C has any children. No, there are no children. Then I move to D. Do D have any children? No, D doesn't have any children. So we just end our algorithm here. So this is how the traversing for a breadth first search will look like. We can implement this using queues, as I mentioned earlier. It can also be implemented using recursion, but it's a bit more complex, using recursion. So I have used queue to explain you what it is. So let's go through the code. Here, we are using queue. So the main idea about, uh, behind using the queue is that in queue you have the queue works in a way which gives you first in and first out features, right? So if you take into account our graph here, um, I can say suppose I'll just explain how the queue works in case of uh, breadth first search. Now we have our root element, we push it to our queue. Now we pop that A and find out all its neighbors. We print that A, and then we find out all of its neighbors. So its neighbors are B, C, and D. So the neighbors are B, C, and D. Now I print B and then look for all of its neighbors. The one of its neighbors is E, so I push E to the queue. Now I pop out C, so I print it and see if C has any neighbors. No, C doesn't have any neighbors. So we move on to D. We pop out D, see if D has any neighbors. No, D doesn't have any neighbors. Then we print E and then we see if E has any neighbors. No, E doesn't have any neighbors. So this is how you traverse, using Q. This is the same output that we got, without using Q and just using our own algorithm that using the same concept, but I have just implemented this using Q. Let's move to the code. The code says that, if the root is none, if there is nothing in the root, we just return it. We create a queue. Here we append the root to it like we did in our graph example. Now, while the length of queue is greater than 0, so while we have elements in our queue, what we are doing it is we are just getting popping the node value, we are printing it, and then you see that if the left is not none, you just add it to the queue, and if the right is not none, you just add it to the queue. So this example is using a tree, so that's why we have left and right pointers. So I'm checking for left and right children. So that's why I have written this. I have checked if the node is not none is because I don't want to, push any null value into my queue. So that's why I'm checking it. And then if there is any value, I'm just pushing it to my queue. Uh, let's talk about the space and time complexity of BFS. The time complexity of BFS is also O of n because we are, processing each element just once. So the time complexity of O of n. Um, with respect to the space complexity of a queue would be O of W, where W is the width of tree. Now let's talk some more about that. So if you see, uh, at some moment, the only number of nodes that are in the queue is gonna be the width of the tree. So what do I mean by width of the tree? So at this particular time, only these many elements are going to be there in the queue, or these many elements. So whichever is the width of the tree, I mean the how many nodes are there on each level, that would be, the space complexity of a breadth first search algorithm. I have used the same tree here where I have 5, 3, 6, 1, 4. Let's try and run this code. So if I run this code, I get 1, 3, 4, 5, 6. Where if you see, I have used the same example here for DFS, and it says 1, 3, 4, 5, 6. So that's correct. I have not used the same one for BFS, but we know that BFS is gonna look like something like 5, then the second level which is 3 and 6, and then the third level which is 1 and 4. So 5, 3, 6, 1, 4. So it says 5, 3, 6, 1, 4. Yeah, so it works. If you want to see this code, I'm gonna upload it to GitHub, and if you want to see the link, it will be right down in the description. Um, if you have any questions or have any any concept that you want me to talk about, please feel free to comment in the comment section and give me a thumbs up if you like this video. And if you want to get such algorithm concepts in the future, please do hit the subscribe button. Um, I'll see you next time. Happy coding.